Welcome to this video. We are going to learn about a Bainbridge spectrometer and how it provides evidence of isotopes. Remember, isotopes are a single element like nitrogen with different masses. Okay, the first component of a Bainbridge spectrometer is an ion source. In this example, we'll imagine that the ion source produces positive nitrogen ions. It doesn't have to be nitrogen, but the important thing is that all of the ions are the same element. The next thing is an accelerating voltage. The ions are produced, they're positive, and once they enter this voltage, they are accelerated from one end to the other. The way we accelerate the ions is with a positive plate and a negative plate, which have a slit in between that ions can pass through. Once the ions have been accelerated, they enter a velocity selector. Ions could potentially have different speeds when they enter the selector, but we want them to all have the same speed. So we use the selector, and that causes only ions with a specific one speed to exit the other side. A velocity selector we've studied already. It has a positive and negative plate. There's a field, an electric field pointing down. But in addition to the downward electric field, there's also a magnetic field, which is crossed or at a right angle to the electric field. The way we know it's crossed is because the X's indicate that the magnetic field is into the page, and going into the page is perpendicular to going down. Okay, so ions are produced, they're accelerated. We only let specific speeds get through, one specific speed. And then those ions, which make it through, enter a large magnetic field. This magnetic field is also into the page, like this one. At the edge of this magnetic field region, there is a detector, which detects ions. Okay, so let's watch the path followed by two different nitrogen ions. Here's what happens, and this is kind of interesting. A first nitrogen might come through like this, and once it enters this region, it feels a centripetal magnetic force. So it moves in a circle, and it hits the detector. But then a second nitrogen comes through, and it does follow a circular path, but this second one follows a larger radius. Why is this happening? Inside of the magnetic field, there is a net centripetal force, which is simply equal to the magnetic force. On the left side, the magnetic force is q, the charge, times that speed, which was selected, times b, the strength of this field. On the right, centripetal net force is equal to m times v squared over r. If we solve for r, we get this equation. Now take a look, because there's something interesting about our setup. The charge is the same for every ion. Our ion source produces ions which all have the same charge. The speed v is the same because the velocity selector only lets through ions with a specific speed. B, the magnetic field strength, is the same because we make this a uniform field. So the only thing that radius depends on, right, these two radii are different. The only thing radius depends on is mass, assuming that these are all constant. Or radius is directly proportional to mass. The entire Bainbridge setup is designed so that this fact is true. That's the crucial fact. So for example, that red path that I just highlighted, it's a bigger radius, so that nitrogen ion has a bigger mass. And this blue path was a smaller radius, so that nitrogen ion had a smaller had a smaller mass. The fact that nitrogens land at different positions on the detector, so for example, the red nitrogen lands right here, and the smaller mass nitrogen lands right there. Those are two different positions. The fact that they land at different positions is evidence of isotopes. They must have different masses because they follow different radii. Okay, so here's what you need to be able to know. You need to draw the ion source, the accelerating voltage, the velocity selector, and the uniform B field. And it's fine to just draw boxes like I've shown. You don't need to put the specific diagram from before. There's also a detector you would want to draw if asked to draw this picture. The key facts are that this spectrometer controls everything but mass. All of the ions have the same charge, they have the same velocity, and thus the radius of their path is proportional to mass. A single element, like nitrogen, or maybe a different element, is ionized. Some ions follow a larger radius, so they come and they have a bigger path. Others have a smaller path, smaller radius. The larger radius indicates a larger mass of ion, and this is evidence of isotopes.